Well, if you're ready.
Yes, please. After a short introduction, we will ask you please to turn your microphones and cameras off until the end of the talk, where you will be able to ask questions, either through questions and answers, or just by opening the microphone. Since you have been promoted to panelists, you can do it, but please don't ask questions during the talk. So I'm very pleased to introduce Professor Burak Özbağcı for an invited talk this afternoon. He received his PhD degree in 1999 from the University of California at Irvine and held visiting positions at several universities in the United States. In 2012, he became a professor at Koç University in Istanbul. He's a specialist in symplectic and contact geometry, as well as topology of smooth manifolds. He has published 40 papers in prestigious journals, and in 2004, he published a Springer book jointly with Andras Stipsix on surgery on contact 3 manifolds and Stein surfaces. He has received grants and prizes from the Turkish Academy of Science, from the US National Science Foundation, and from the European Research Council, as well as a large number of outstanding research and outstanding teaching awards. Congratulations. Moreover, since 2019, he's president of the Turkish Mathematical Society. It is a great honor for me to chair his talk on topology of symplectic fillings of contact 3 manifolds. Professor Özbağcı, please go ahead.
Thank you for the introduction, Carlos. So first of all, I would like to thank the organizers for the invitation to speak here. It's a great honor to speak at the European Congress, and it's my first time attending to the conference, unfortunately via Zoom. So today I'll talk about the topology of symplectic fillings of contact 3 manifolds. So at the turn of the century, there were 2 groundbreaking results about symplectic and contact topology in low dimensions. Well, most of it is true in higher dimensions, but today I'll just focus on low dimensions. The first one is Donaldson's result about the existence of Lefschetz pencils on closed symplectic 4 manifolds, and the other one is Joule's correspondence between open books and contact structures on closed 3 manifolds. So let me start with topological characterization of symplectic 4 manifolds as a result of Donaldson's pencils. So let's start with the definition of Lefschetz fibrations. Suppose that X and sigma are compact, oriented, and smooth manifolds of dimensions 4 and 2 respectively, possibly with non-empty boundaries. Lefschetz fibration pi from X to sigma is a submersion, except for finitely many points P1 up to Pk in the interior of X, such that around each Pi and their image pi Pi, there are orientation preserving complex charts on which pi is of the form Z1, Z2 mapping to Z1 squared plus Z2 squared. So the topology of Lefschetz fibrations is well studied and well understood. There's a lot to say about the topology of the 4 manifold X. Let me just say just one important basic topology of the 4 manifold X. Lefschetz critical points, which are the critical points P1 and Pk in the definition, can be viewed as complex analogs of Morse critical points, and they correspond to 2 handles. As a result, one obtains a handle decomposition of X, and one can even draw Kirby diagrams of these 4 manifolds. Lefschetz fibrations can also be described combinatorially by means of their monodromy. Locally, the fiber of the map Z1, Z2 mapping to Z1 squared plus Z2 squared above a non-zero complex number is smooth, topologically and analogous, while the fiber above the origin has transverse double point, which is also called the nodal singularity, and is obtained from the nearby fibers by collapsing an embedded simple closed loop called the vanishing cycle. So here's a schematic picture that you will see in many of the Lefschetz fibration talks. So sigma is the base surface. In this case, I drew one without a boundary. The regular fiber does not have a boundary either. Here is a vanishing cycle. It's a loop on the regular fiber. When you collapse it to a point, you get your singular fiber, which is supposed to be nearby. And at this point, there's a nodal singularity, a node, which is the intersection of two complex planes in the force space, which you can only represent in 2 dimensions like this. All right, so let's talk more about the monodromy. Given a Lefschetz vibration pi from x to sigma, fix a loop in sigma enclosing a single critical value whose critical fiber has a single node. Then pi restricts the surface vibration over this loop because there is no singularity, whose monodromy, a diffeomorphism of the fiber, is given by the right-handed Dane twist about the vanishing cycle. So here I depict a vanishing cycle and a neighborhood of it, which is an annulus drawn like a cylinder. And a Dane twist can be explained without formulas like this. So you take an arc connecting 2 boundary components of the annulus, and the image of that arc is presented on the right-hand side. It picks up a right twist, and the endpoints are fixed. Therefore, it fixes the boundary of this annulus. It's a diffeomorphism which can extend to the whole surface by the identity. For the purposes of this talk, we restrict our attention to the cases where either sigma is a 2-sphere, S2, and the fibers are closed surfaces. Therefore, the boundary of X is empty. Or sigma is a 2-disk, and the fibers have non-empty boundaries, and therefore the form manifold has non-empty boundary. In both cases, we also assume that each singular fiber carries a unique singularity, and there are no homotopically trivial vanishing cycles, which will be standing assumptions for the rest of the talk. First case, when sigma is S2 and the boundary is empty, if Q1 up to Qk in the sphere are the critical values of a genus G Lefschetz vibration, where genus G means that the fiber is of genus G, then by fixing a point Q0 in the base S2, we can characterize the vibration by means of its monodromy morphism psi, which goes from pi1 of S2 minus the critical values to map G, where map G is the mapping class group of an oriented closed genus G surface. So here is typically what you would see in the base. So in the base space, here is what you're looking at is a disk, and it's actually a sphere, and there's a disk on the other side. From Q0, you make loops which goes around these critical values once and comes back. Each one of them in the monodromy is a right-handed Dane twist. If you compose them Q1 up to Qk, you would get a product of positive Dane twists, which should be isotopic to the identity, because on the other side of the disk, there's a trivial vibration. And therefore, the upshot of this discussion is a Lefschetz vibration from a form manifold onto S2 is characterized by a positive Dane twist factorization of the identity element in map G. Well, this is uniquely determined up to some natural equivalences, which I don't want to go into because of the time restriction. Second case is when sigma is a disk and the boundary is non-empty. So the form manifold has boundary and the fibers will have boundary in general. This case is simpler since the global monodromy is a product of positive Dane twists in map GR, the mapping class group of a genus G surface with R boundary components with no other constraints. So here is how I would picture this. This is a regular fiber. It has 2 boundary components. And this is a singular fiber, which is obtained from the regular fiber by collapsing a separating vanishing cycle, which I didn't draw here. In this case, boundary of X inherits a natural open book decomposition, which we will discuss in details later in this talk. Now let me briefly say what is a Lefschetz pencil. A Lefschetz pencil on a closed and oriented form manifold X is a map from X minus a finite number of points, B1 up to Bn, which is called the base locus, onto S2, which is again submersive except for a finite set P1 up to Pk, conforming to local models. Z1, Z2 is mapped to Z1 mod Z2 near each base points, Bi, and near each Pj, the critical points, it is like the Lefschetz critical points. So essentially, a Lefschetz pencil is a Lefschetz vibration on the complement of finitely many points, B1 up to Bn, where there is a certain local model near these base points. So typically people draw Lefschetz pencils like this because of the dimensional reasons. So these black arcs in the picture will represent smooth surfaces, and the green arc represents a singular surface with a singularity. It will be a singular fiber of the pencil. The pink dots here represents the base locus. So all these surfaces, the regular ones and the singular ones, they all go through these base points, which is called the base locus. By blowing up X at the base points B1 up to Bn, we obtain a Lefschetz vibration on X blown up n times. Topologically, this means that I take the connected sum of X with n copies of CP2 bar, which is the complex projective space, complex projective plane with the reversed orientation onto S2 with n disjoint sections, which are the exceptional spheres in the blow up. So these in the blow ups, there are exceptional spheres, which will appear as disjoint sections of this vibration. So here is the summary. We have a Lefschetz pencil on the left-hand side. There's the base locus, the pink dots. We blow up those points. Those purple points become exceptional spheres in the Lefschetz vibration. So the base is now a sphere, a smooth surface. Four manifold X is represented up here. These are regular fibers, and this is a singular fiber. So except for finitely many fibers, all the fibers are smooth. And there are finitely many fibers which are singular, which is Lefschetz type singularity. All right, so all of this started with Lefschetz himself. In 1924, Lefschetz showed that projective surfaces admit Lefschetz pencils, which is the result that was extended by Donaldson to all closed symplectic four manifolds. Those, these manifolds admitting closed non-degenerate two forms. So the theorem that I mentioned at the beginning of my talk is a theorem of Donaldson from 1999, which says that any closed symplectic four manifold admits a Lefschetz pencil in very simple terms. Conversely, Gompf, around the same time, generalizing a similar result of Thurston from 76 on surface bundle over surfaces, showed that if pi x to sigma is a Lefschetz vibration for which the fiber represents a non-torsion homology class, then X admits a symplectic structure with symplectic fibers. Compared to Donaldson's result, this is relatively simpler. Donaldson's result is a much deeper one. The hypothesis here is satisfied if the fiber genus is not equal to 1. It's not a serious restriction, but it's necessary. It's a necessary condition. As a corollary, Gompf showed that any closed form manifold which admits a Lefschetz pencil is in fact symplectic. So putting together this topological characterization of symplectic form manifolds, meaning that a closed form manifold is symplectic if and only if it admits a pencil, has led to a renewed interest in Lefschetz pencils and fibrations, and hundreds of papers to this day have been devoted to the study of various aspects and generalizations of Lefschetz fibrations. Here is one of the earlier results. Well, this is my first published paper. It's joint work with Andreas Stupschutz, and this was independently obtained by Ivan Smith. The theorem is that there are infinitely many pairwise non-homeomorphic closed form manifolds which admit genus 2 Lefschetz fibrations over the sphere, but do not carry complex structure with either orientation. So, the point of this theorem is that it was clear that these are more general than just the complex surfaces, just the Kähler surfaces. And this example gave explicit such four manifolds not admitting complex structures, but having genus 2 Lefschetz fibrations. Genus 2 is the minimum we can go here because we understand well genus 0 and genus 1 fibrations. These examples are obtained by fiber sums of genus 2 Lefschetz fibrations on S2 cross T2, blown up 4 times, which are due to Matsumoto. So these are in this Lefschetz vibration, in this genus 2 Lefschetz vibration, there are 8 singular fibers, there are 8 vanishing cycles. And if you take a fiber sum, meaning that if you remove 2 fibers from each and glue the resulting boundaries, This is what's called a fibersome. It is still a genus 2 fibration. And in this case, you obtain one which is non-complex. So as a corollary, this also shows that fibersums of holomorphic Lefschetz fibrations is not necessarily holomorphic, because Matsumoto's fibration comes from a holomorphic map. And when you take the fibersums, you lose the holomorphicity of the fibration because the total space is not complex. So there is a lot more to say about these fibrations, classifications, but it's a long list and hundreds of papers are written on the subject, and I cannot go through all of them, but maybe I should mention the result of Denis Arroux about stable classification of Lefschetz fibrations, which I didn't write on the slide. All right, now let's turn the page and talk about topological characterization of contact 3 manifolds. This is very similar story to Lefschetz fibrations. It's a dimension reduction, essentially. So fibrations in 4 dimensions reduces the problems to fibers, which are 2-dimensional. We will do the same thing in 3 manifolds, and we reduce the question to 2 dimensions by what's called open book decompositions. An open book decomposition of a closed and oriented 3 manifold is a pair B pi consisting of an oriented link B and a locally trivial fibration in the complement of B, such that B has trivial tubular neighborhood, which is B cross D2, in which pi is given by the angular coordinate in the D2 factor. Here, B is called the binding, and the closure of each fiber, which is a ciphered surface for B, is called the page. It will be clear in the next slide why this is called an open book. So here is a schematic picture of an open book. So binding is a link in the 3D space, 3-dimensional manifold, and the pages have boundary exactly the binding, and it is supposed to look like an open book, as I tried to illustrate in this slide. So let's have a more concrete example rather than schematics. So this is Milner's fibration. Consider the polynomial f from C2 to C given by Z1, Z2 mapped to Z1 to the P plus Z2 to the Q, where P and Q are coprime. Then B, which is F inverse of 0 intersection the unit sphere in C2, is the PQ torus knot in S3, whose complement fibers over the circle. The fibration is F divided by the norm of F. It's a unit complex number, and the fact that this is a fibration is a theorem of Milner in much more generality. So B pi here is an open book for S3 with connected binding. Here is a schematic picture of that. Actually, this is, you see in the background, a torus, and I drew a knot, a torus knot on the torus, which is a 2-3 torus knot. And this is known as the trefoil. And Miller's fibration says that the complement of the trefoil fibers of the circle, whose fiber is actually a genus 1 surface. The topology of an open book in general is determined by the topology of its page and its monodromy. We choose a vector field which is transverse to the pages and meridional near the binding. The isotopic class of the first return map on a fixed page is the monodromy of the open book. So now let's relate these discussion with the Lefschetz fibrations. Suppose that X to D2 is a Lefschetz fibration such that the regular fiber F has non-empty boundary. Then boundary of X is the union of 2 pieces, the horizontal boundary, which is boundary F cross D2, and the vertical boundary, which is the inverse image of boundary D2. They're glued together along the tori boundary F cross boundary D2. Right? So if F has more than one boundary components, you would have more than one tori in this gluing region. It follows that boundary of X inherits a natural open book, whose page is the fiber F, and whose monodromy coincides with the monodromy of the Lefschetz fibration. So let me try to illustrate this. The vertical boundary will be pi inverse of the boundary of the base disk. This is the base disk, and there is the boundary. Above each point, there is the surface. It's a surface fibration so far. This is one part of the boundary, which is vertical because of it looks, vertically in this presentation. And there's a horizontal boundary, which sort of looks like this. So we have the disk, And above the disk, every fiber, regular and singular, will have exactly the same boundary F, maybe more than one component, but then the disk cross that boundary will be a part of the boundary of the form manifold, which is the boundary F cross D2. Together, that gives you an open book decomposition. So let's talk about contact 3 manifolds very, very briefly. A differential one form alpha on a manifold Y is called a contact form if alpha which D alpha is a volume form. A two-dimensional distribution psi in the tangent bundle is called a contact structure if it can be given as a kernel of a contact one form alpha. And the pair Y psi is called the contact 3 manifold. So there is a result which is known as the Darboux theorem, which says that there are no local invariants of a contact manifold. So any point in a contact 3 manifold has a neighborhood isomorphic to a neighborhood of the origin in the standard contact structure psi given as a kernel of dz plus x dy in R3. So locally, you cannot distinguish contact 3 manifolds and contact manifolds in general. So let me draw this, show you this picture of planes, contact planes in the standard contact structure. So this is along the x-axis, and I show you the planes along the x-axis. There is one which is horizontal, the way that we look at it, it's horizontal, and it rotates as you go along the positive x-axis. Since the form is independent of y, then along every axis parallel to the x-axis, you will see exactly the same thing. And we're done with the xy plane, and all in all the planes parallel to the xy plane, you will see a copy of this. Right? You fill in the space with these planes, which is called the standard contact structure, and every contact 3 manifold actually looks like this locally. So what is the relation between open books and contact structures on 3 manifolds? There is a relation in higher dimensions as well, but today we focus on dimension 3. It's a theorem of Alexander from 1923, almost 100 years ago. That every closed 3 manifold has an open book decomposition. And the theorem of Martinez says that every oriented 3 manifold has a contact structure. In 1975, Thurston and Winke and Kemper noticed that they can actually construct contact forms on closed 3 manifolds using open books, giving an alternate proof of Martinez's theorem. So the proof of Martinez originally is very different from this. And it was an idea of Thurston and Winke and Kemper, a very short paper where they introduce how you can actually construct contact forms using open books, just like Thurston did put symplectic structure on a fibration, a surface fibration over a surface. And maybe I should mention that Winke and Kemper was the first person using the name open books. It was in his PhD thesis, and he coined this name open books for such objects. So based on this description of Thurston and Winke and Kemper, we can actually relate contact structures and open books in a concrete definition as follows. We say that the contact structure psi on Y is supported by an open book B pi if psi can be given by a contact form alpha such that alpha evaluates positively on the binding and D alpha evaluates positively on every page, making every page symplectic. So we can rephrase the theorem of Thurston and Winke and Kemper as follows. Every open book on a closed oriented 3 manifold supports a contact structure. So based on this definition, we can reformulate it exactly in this way. The question is the converse, the hard part, which is that every contact structure on Y is supported by an open book. This was proven by Giroux around the turn of the century. This was in the first slide that I referred to as the groundbreaking result in 3-dimensional contact topology. So in fact, he proved much more. He proved something called Giroux's correspondence, which says that on a closed oriented 3 manifold, there is a one-to-one correspondence between the set of isotopic classes of contact structures and the open books up to positive stabilization. So these equivalences on both sides, contact structures and open books, are natural equivalence classes, and they appear naturally in this correspondence. All right, so now let's talk about back to four manifolds back to complex manifolds. In fact, we will talk about Stein manifolds. A Stein manifold is an affine complex manifold. In other words, it's a complex manifold that admits a proper holomorphic embedding into some Cn. There is a characterization using Morse functions on complex manifolds due to Grauert. So let me explain that characterization. But before, I need to say a few more definitions. If phi from X to R is a smooth function on a complex manifold Xj, J denotes the complex multiplication, which is the endomorphism of the tangent bundle, then omega sub phi, defined as minus the differential of d phi composed with J, is a two form. And the map phi from X to R is called J convex, also known as strictly plurisubharmonic, if omega phi uju is positive for all non-zero vectors in Tx. It follows from this definition that omega is in fact an exact symplectic form on X. So Stein manifolds are exact symplectic, and in fact they are Kähler manifolds. So now I can state Grauert's characterization using these J-convex functions. A complex manifold Xj is Stein if and only if it admits a proper J-convex function phi from X to non-negative real numbers. This opens up the possibility of using these functions to study topology of the Stein manifolds. So for the purposes of this talk, we now restrict our attention to Stein surfaces, which are complex two-dimensional manifolds. Let Xj be a Stein surface. For any J-convex Morse function, which you can always assume that it's Morse, each regular level set Y of this function phi is a contact 3 manifold, where the contact structure is given by the kernel of alpha, which is minus d phi composed with J. It's the primitive of omega, or equivalently by the complex tangencies Ty intersection JTy. For any regular value C of phi, the sublevel set W, which is phi inverse of the closed interval from 0 to C, is called a Stein domain. We also say that the compact form manifold Wj is a Stein filling of its contact boundary, W, the boundary of W, and psi being the kernel of alpha, which is equivalently the complex tangency. So next I want to talk about topological characterization of Stein domains. This is sort of the main part of the talk. There's a topological characterization of closed symplectic form manifolds, closed contact 3 manifolds, and there's also one which is given by Lefschetz fibrations that I want to explain. By the work of Eliashberg and Gompf, Eliashberg in the 90s in general dimensions, and Gompf in dimension 4 in particular, handled the composition of a Stein domain, again in dimension 2. Stein domain Wj is well understood. It consists of a 0 handle, a 1 handle, some 1 handles, more than one, and this part is sort of standard. There are not too many choices, and some 2 handles attached along Legendre knots, the knots which are tangent to the contact planes in the boundary of the result of 0 and the 1 handles, with framing -1 relative to the contact planes. This is very well understood, and you can actually draw diagrams which represents these Stein domains. And based on this, Akbulut and myself, and independently Loya and Piergalini, gave 2 different proofs of the following theorem. A Stein domain admits an allowable Lefschetz fibration over the disk, and conversely, an allowable Lefschetz fibration over the disk admits a Stein structure. So this gives a complete characterization of Stein domains in terms of Lefschetz fibrations, just like the symplectic manifolds and the contact manifolds. So here, allowable means that the vanishing cycles are homologically non-trivial. This is a necessary and sufficient condition. So idea of the proof is in a nutshell that Stein 2-handle is nothing but a Lefschetz 2-handle and vice versa. But I try to simplify the proof that on the one hand, you attach Stein 2-handles. These are the critical ones on this side. And on the side, left-shift handles, two handles are the critical ones, and you can sort of make sure that they are the same, and this is the idea of the proof. Moreover, by slightly modifying the proof of Akbulut and myself, Klemenevskaya showed that the context structure induced on the boundary of the Stein domain is supported by the open book inherited by the left-shift vibration. So altogether, we have this diagram. Stein domains are allowable left-shift vibrations and vice versa. And if you take the boundary of the allowable left-shift vibration, you get an open book. If you take the boundary of the Stein domain, you get a context structure. And these two, the context structure and open book, are also compatible in the sense that the context structure is supported by the open book. So an outcome of this is the following. A criterion for Stein fillability. A context three-manifold is Stein fillable if and only if it admits a supporting open book whose monodromy can be factorized into positive gain 2s. But it's completely a topological characterization of Stein fillability. This was also independently proven by Giroux using only three-dimensional methods rather than an outcome of left-shift vibrations. An active line of research topic in symplectic and context topology is to classify all Stein fillings, or more generally, all minimal symplectic fillings of a given context three-manifold up to diffeomorphism and even up to deformation of the symplectic structure. So a compact symplectic manifold X omega is a strong symplectic filling of a context three-manifold Y psi if boundary of X is Y. Omega is exactly near the boundary, and its primitive alpha can be chosen so that kernel of alpha restricted to Y is psi. This is more general than just the Stein fillings. Stein fillings are examples of this type where the form is exact on the whole space. I should also give the definition of minimality. A symplectic filling is called minimal if it does not contain any symplectically embedded sphere of self-intersection -1. And we would like to classify minimal symplectic fillings because you can always blow up a symplectic manifold to get another symplectic manifold, and there are infinitely many ways of doing that. Therefore, we would like to restrict our attention to minimal symplectic fillings. Every Stein filling is a minimal symplectic filling. This follows automatically from the definitions, immediate from the definitions, but the converse is not true, as shown by Gigini, using the powerful Özbağcı contact invariance. So this part, it was difficult and finally proven by Gigini by giving examples. The classification of Stein and more generally minimal symplectic fillings of a given contact three-manifold is difficult in general. There are many techniques coming from holomorphic curves. Nevertheless, this problem has been solved for many contact three-manifolds, each of which has finite many fillings. Again, there's a list of people who worked on this subject, and I don't have time to list all of them. But the first example of a contact three-manifold which admits infinitely many distinct Stein fillings was given by András Stipchitz and myself. Let me explain this example. Let YG denote the closed three-manifold, which is the total space of an open book whose page is a genus G surface with connected boundary, a very simple object so far, and whose monodromy is the square of the boundary Dane twist. I just take this very simple three-manifold described by an open book. Let psi sub G denote the context structure on this manifold supported by this open book. We proved with András Stipchitz that for each odd integer G greater than or equal to 3, the contact three-manifold YG psi G admits infinitely many pairwise non-homeomorphic Stein fillings. These were the first example of this type, showing that it's hopeless to try to classify the fillings for every contact manifold because some of them have infinitely many Stein fillings. Let me say outline of proof. A positive word in map G for G greater than or equal to 3, generalizing Matsumoto's genus 2 word, was discovered by K. David and Mustafa Korkmaz independently. And the word looks like this. For odd G, it looks like the product of Dane twists along these curves, C0 up to CG, A and B, and then squared is equal to 1 in the mapping class group of genus G. So here are those curves. Just to give you an idea, like these curves C0 up to CG are represented here, C0 going all the way to CG, and A and B are the standard curves. This is a genus G surface, and the product of these gain twists is exact identity in the map and class group. So using this relation, we can construct the Lefschetz vibration of the sphere. Then we take twisted fiber sums of Lefschetz vibrations, 2 copies of these. Twisted means that when you do the fiber sum, you use a diffeomorphism different from the identity. That's sort of the critical point of this outline. Then you remove a section and a fiber to get Stein fillings, infinitely many of them, because you have infinitely many choices of twisting in this fiber sums, of the common contact boundary. The common contact boundary is described by this open book that I told you in the previous slide. And we distinguish the Stein fillings by torsion in the first homology of the total space coming from the twisting. So this twisting of the fiber sums here introduce torsion in the first homology of the four manifold, and therefore we can distinguish them immediately. Well, I should mention a more recent result of Inanç Baykur and Jeremy Van Horn Morris, where they showed that there are vast families of contact 3 manifolds, each member of which admits infinitely many Stein fillings with arbitrarily large Euler characteristics and arbitrarily small signature. So based on the first examples in the subject, people thought, maybe Andraj and I thought that the Stein fillings have finite topology. This was the case in the previous slide, but it turns out that it's not the case, and you can have arbitrary topology of Stein fillings for a fixed contact 3 manifold. So it's completely hopeless to try to classify Stein fillings for these kind of 3 manifolds. All right, so now let's turn to canonical contact structures on the links of isolated complex surface singularities. So there's a relation between this contact structures, Lefschetz vibrations, and surface singularities. A fruitful source of Stein fillable contact 3 manifolds is given by the links of isolated complex surface singularities. Let X be an isolated complex surface singularity sitting in Cn. Then for a sufficiently small sphere centered at the origin, X intersection the sphere is a closed, oriented, and smooth 3-dimensional manifold, which is called the link of the singularity. And if J denotes the complex structure on X, right? So it's only singular at a point, it's regular at other points, there's a complex structure. Then the complex tangencies, Ty intersection JTy, is a contact structure on Y, which is called the canonical, otherwise known as Milnor fillable contact structure on the singularity link. So we refer to this pair Y psi as the contact singularity link in short. Note that psi is determined uniquely, independent of the analytical structure. It's just topological. It's determined uniquely up to isomorphism by a theorem of Kubel, Nemeti, and Popescu-Pampu. So therefore, one can speak about the fillings of this contact manifold independent of the analytic ways of filling the same topological 3 manifold. The minimal resolution of the singularity provides a Stein filling of the contact singularity link. This is by the work of Bogomolov and de Oliveira. There's a subtle point here. The fillings are initially holomorphic fillings, but you can make them Stein, and that deformation is defined by Bogomolov and de Oliveira. Therefore, any contact singularity link is Stein fillable. Moreover, if the singularity is smoothable, it's a very long discussion what this means, but if you can deform the singularity so that the surface becomes smooth, then the general fiber X of a smoothing is called a Milnor fiber, which is a compact smooth 4 manifold such that boundary of X is equal to Y. Furthermore, X has a natural Stein structure so that it provides a Stein, hence minimal symplectic filling of Y psi. A natural question arises. So this was raised a while ago. So does there exist a contact singularity link which admits Stein or minimal symplectic fillings other than the Milnor fibers and the minimal resolution? So how far you can go with symplectic techniques, but not using complex algebraic techniques? What is the difference in terms of their fillings? The answer is no for simple and simple elliptic singularities. This is proven by Ahta and Ona. And no for cyclic quotient singularities. There's a long list of people who contributed to this problem. I wrote the names and the dates. No for non-cyclic quotient singularities. Again, there's a long list of people who contribute to this. But yes, for some Seifert-Fibert singularity links, as shown by Anar Ahmedov and myself. So these were the first examples of contact singularity links, which admits fillings other than the Milnor fibers and the minimal resolution. So let me state the theorem with Ahmedov. There exists an infinite family of Seifert-Fibert contact singularity links, such that each member of this family admits infinitely many exotic Stein fillings. And moreover, none of these Stein fillings are homeomorphic to Milnor fibers. Exotic here means homeomorphic, but pairwise not diffeomorphic. And I should point out that our examples are not simply connected. The first examples of infinitely many exotic simply connected Stein fillings were discovered by Ahmedov, Edmeyer, Mark, and Smith. So more recently, probably you heard of this, some of you are experts on the subject, Plemenevskaya and Starkston. This here showed that many rational singularities admit simply connected Stein fillings, which are much harder to distinguish because you don't have the homology, the first Bethe number to distinguish them, that are not diffeomorphic to any Milnor fibers. Their techniques are slightly different from what we use with Anar. So let me also mention another theorem with Anar Ahmedov. For any finitely presented group G, there exists a context singularity link which admits infinitely many exotic Stein fillings, such that the fundamental group of each filling is G. So this is in much more generality. We proved this thing that you can have these infinitely many exotic fillings with the same group G. Some key ingredients in the proofs. We use Luttinger surgery, a technique in surgery in 4 dimensions, which is a generalization of Dane surgery. Symplectic sum, a common method in symplectic form manifold techniques. Fintelstein knot surgery, and the Seiberg-Witten invariance to distinguish the exotic copies. Now I want to turn your attention to Lefschetz vibrations on minimal symplectic fillings of length spaces. I'm running out of time, but I'll take maybe 5 more minutes.
Yes, please go ahead.
Thank you. Let Xi denote the canonical context structure on the length space LPQ, which is the link of a cyclic quotient surface singularity. The minimal symplectic fillings of LPQ Xi with this canonical context structure has been classified by Liska, and this is based on the work of McTaff from 90s, where she already classified LP1 Xi. A theorem of Mohan Bhupal and myself, we proved in 2016, says that there is an algorithm to describe any minimal symplectic filling of LPQ Xi as an explicit genus 0 allowable Lefschetz vibration over the disk. Genus 0 is the part that I emphasize. So clearly, these minimal symplectic fillings are Stein fillings, and therefore they admit Lefschetz vibration over the disk. But the point that they're genus 0. Moreover, using this, we prove that any minimal symplectic filling of LPQ Xi is obtained by a sequence of rational blowdowns starting from the minimal resolution of the corresponding cyclic quotient singularity. So the second part was more interesting because this was not known, and this sort of shed light to all minimal symplectic fillings of a length space after Liska's classification. So rational blowdown here is a surgery operation discovered by Fintischel and Stern, where a negative definite linear plumbing submanifold is replaced by a rational 4-ball. And this result of Mohan Bhupal and myself was extended to cover the case of non-cyclic quotient singularities as well by Troy and John Park very recently. Although we have not used it in our proof, it also follows by a theorem of Wendell that each minimal symplectic filling of LPQ Xi is in fact deformation equivalent to a genus 0 allowable Lefschetz vibration over the disk. It's a general theorem of Wendell, which is based on planarity. In this case, it is because LPQ Xi is known to be planar, which means that it admits a planar open book that supports Xi. So when you have a planar open book, then the Wendell proved that all Lefschetz fibrations coming from one single open book by factorizing its monodromy in different ways gives you the set of all minimal symplectic fillings of that contact 3 manifold, which is a very powerful and effective theorem in the subject. Now, finally, let me mention Lefschetz fibrations and trisections. The whole talk today was about decomposing 4 manifolds and 3 manifolds in different ways. There's one more that appeared recently, which is called trisections. I'll give the definition of a trisection in very low technical terms. A handle body is a compact manifold admitting a handle decomposition with a single zero handle and some one handles. So in different dimensions, you have different, of course, zero and one handles, but the definition of the handle body is just this, this decomposition. The trisection of a closed 4 manifold X is a decomposition of X into 3 4D handle bodies. So the pieces are very simple, only 4D handle bodies, 3 of them, whose pairwise intersections are 3D handle bodies, and whose triple intersection is a closed embedded surface. This gives a decomposition of the 4 manifold with these very simple pieces, and the complication occurs when you have to describe how they are glued together. This is analogous to Haggard's splitting of a closed 3 manifold, which is a decomposition into 2 3D handle bodies, as most of you know, whose intersection is an embedded surface. So trisections can be presented by trisection diagrams, similar to the Haggard diagrams. In fact, it's sort of a generalization of the Haggard diagrams that gives you complete diagrams which describes these decomposition of X into 3 4D handle bodies. So in the subject, the main theorem is due to Gay and Kirby. Every closed-oriented 4 manifold admits a trisection. So immediately after this result, Gay himself also constructed a trisection directly from a given Lefschetz pencil, but without describing an explicit trisection diagram and not necessarily referring to the vanishing cycles of the fibration of the pencil. In a joint work with Nick Castro, we obtained an alternate proof of the theorem of Gay and Kirby using Lefschetz fibrations and contact geometry, which is sort of in the spirit of what I was talking about today. And we proved the following. Suppose that X is a closed-oriented 4 manifold, which admits a Lefschetz fibration over the sphere with a section of square -1. For example, if it comes from a left pencil, then it will satisfy this condition. Then an explicit trisection of X can be described by a corresponding trisection diagram, which is determined by the vanishing cycles of the Lefschetz fibration. So anytime you have an explicit description of the vanishing cycles of a Lefschetz fibration, then you can construct these diagrams. I should also mention that Inanç-Baykur and Sayaki, around the same time, but published earlier, obtained an alternate proof of the theorem of Gay and Kirby, setting up a correspondence between broken Lefschetz fibrations, which I didn't have time to discuss, but it's a main part of the topic in 4 manifold topology. Broken Lefschetz fibrations and trisections using a method which is very different from ours. So their method uses generic maps and much more sophisticated than what we did with Nick. So they also proved a stronger version of our result that I cited over here. They don't need this section. They can turn Lefschetz fibrations, even broken Lefschetz fibrations, into trisections and vice versa. So I want to finish with this example. A trisection diagram for the Horikawa surface, which has a name H'1, a simply connected complex surface of general type, which admits a genus 2 Lefschetz fibration over sphere with 40 singular fibers. In fact, it's an exotic copy of 5CP2 blown up 29 times. So here is the diagram that we drew with Nick Castro. Well, it's supposed to be a surface of genus 46, and these curves represents the trisection in a certain way. And this is where I'll stop. Thank you very much.